In this video, we're going to be taking a look at sentiment analysis and word embeddings. One of the primary applications of machine learning is sentiment analysis. And the way sentiment analysis works is you try and judge the tone of a document. And so rather than having someone read through it and classify it as being positive or negative, we can get machines to automatically do that. And this is useful in, say, taking a look at the tweets of traders in order to determine the overall market mood, right? Whether people are too optimistic or pessimistic, and thus you could derive value by doing that. And so, as one might expect, sentiment analysis is a natural language processing problem, and NLP for short is a subfield of artificial intelligence that deals with the understanding and processing of language. The goal of this article will be to construct a model to derive the semantic meaning of words of documents within a corpus. And unfortunately, the problem isn't as simple as it sounds, as we'll see shortly. And so to start off, we're going to go ahead and import the following libraries. We're going to go ahead and specify a max number of words. And so this is the cutoff point. Basically, we're only going to take the 10,000 most commonly used words, and this will help simplify the problem. We're going to be using the IMDb dataset, and this contains... Alright, let's try that again. Okay, it's just because I have to use this workaround right now because there's a bug. But anyway, so the data set contains 25,000 reviews, and the testing set contains another 25,000 reviews, and they have an equal number of positive and negative reviews. So by default, the documents that were given, the words in the documents, are already encoded as integers. And if we wanted to take a look at what that looked like in text, we could use the dictionary from the getWordIndex method. And you can see we have a review right here, which is "This film was just brilliantly casting, blah, blah, blah." One thing that I want us to note right here is that the length of the first training sample and the length of the second training sample differ. And before we go ahead and feed the data into our machine learning model, which is going to be a neural network, we have to make sure that the documents are the same length. So we'll get into that in a second. So yeah, we're going to use the pad sequence method to basically put in filler tokens or words or whatever you want to call it for the shorter documents. And so we're going to ensure that all the documents have a length of 256. So we'll go ahead and run that, and then if we take a look, you can see now that the first sample and the second sample have the same length. So, as the attuned reader might have guessed, the words are categorical features. And so a categorical feature is when you're working with data that where one of the features is best described as categories or words. So an example might be like a place. So let's say you're taking a look at housing prices. Well, you might have the location of the house by city, let's say. And for your model to interpret that, you would have to encode that into numbers. Now, typically, we don't want to use integers because if we do that, our model will interpret the integers with a higher value as having higher priority, when in reality, all the categorical features have the same priority, right? So Ottawa and Toronto shouldn't be interpreted differently. And the way we normally get around this is by using one-hot encoding. And in one-hot encoding, you distinguish between the categorical features by having a 1 in a specific location and then zeros in all the other locations. Now, in the case of, in our case, if we were to do that, we would end up wasting a lot of space. The reason being is that we have 10,000 words, and so 10,000 categories. And if we need to store each of those multiplied by all the other instances, right? So we would have 1 1 and then 9,999 zeros into RAM in order to train our model. And so that's obviously not optimal. And so what we can do instead is we can use word embeddings. And basically how word embeddings work, is they will reduce the number of dimensions by mapping words to embedding vectors. And so let's take a look at an example. Suppose we have the following sentences. So we have hope to see you soon and then nice to see you again. Just like what the IMDb dataset did, is we can encode each of these words as a unique integer. So hope would be given 0, 2 would be mapped to 1, C would be mapped to 2, U 3, and then soon 4, and again 6. And what we can do is we can specify a embedding layer. And so the embedding layer has 3 inputs that we're giving in this case. So the input dimension, so that's the size of your vocabulary. So here we have 7 unique words, and so our input dimension will be 7. The output dimension is the size of the embedding vectors, which we'll get to in a second. And then the input length is the length of the sentences that you're feeding into it. And so here each of our sentences are 5 words long. So basically every token, in this case word, will act as an index which stores a vector. And so if we look here, the 0 index, which is associated with the word hope, has the following embedding vector. And the way it works is, it can best be described with this example. So let's say we had the word teacher, and it had the associated embedding vector right here. What we would do is we would, you can imagine a 2-dimensional graph where we have all these different words, and the embedding vectors give you a location in that 2-dimensional space. And so the word teacher will end up in close proximity to the word school as well as tutor, but all of these will be far away from the word food. Okay, and your model will actually train and learn these embeddings much the same way as it would the weights. And so what we'll end up doing is, in our case, we'll use a 16-dimensional embedding vectors, so rather than 2. And we might find words like and fantastic in close proximity to one another. And then our model can learn to classify the reviews with those embedding vectors, or the values, right? The values of the embedding vectors should be close, as positive. And so we can go ahead and create our model right here. We'll compile it, and then we'll train it. So this is going by pretty quickly, so I'm not going to bother pausing the video. Okay, so now let's take a look at our validation loss and validation accuracy. So you can see here that as we trained our model, the training loss decreased and the validation loss decreased, which is good. And the same thing with accuracy. As we trained our model, the accuracy went up and the validation accuracy went up as well. And I think we got as high as, yeah, close to 95%, which is pretty good. So next, we're going to take a look at our testing accuracy, and we managed to get 88% accuracy on the testing set. So there's a bit of overfitting, but still pretty good, all things considered. And so in conclusion, when you have a lot of categorical variables, i.e. you're working with words, we want to avoid using one-hot encoding because this will require a large matrix in memory, and it will require you to train a lot of parameters. So instead what we can do is we can use a word embedding in order to reduce the number of dimensions we're working with and train our model that way. So thank you for watching. If you have any questions, let me know in the comments.